Hello everyone, welcome to our presentation at the Hack in the Box conference. Today our topic is The Art of Exploiting User-Free by Ret2bpf in Android kernel. My name is Xingyu. I am a security engineer at Google. I play Veracity, do reverse engineering and hunt Android kernel bugs to make Android ecosystem more secure. Richard Neal is my colleague and he is a staff security engineer and also manager. Richard likes reverse engineering, especially for reading disassembly. So today we would like to present a deep dive into a specific Android kernel vulnerability discovered this year. And more specifically, it's a user-free bug that has existed in Android common kernel for years. Here's our agenda. We will introduce the internals of the affected kernel module in the Android common kernel, including the passive vulnerabilities, and then analyze the user-free bug CV 2021-0399. We will later talk about how to exploit the vulnerability on a modern Android device, including a video demo. Richard will talk about Android kernel mitigations and how Google detects and exploit code at scale by various approaches. Okay, so let's take a look at the affected Android kernel module xt_qtagid. The module is mainly used for tracking the network traffic on a per-socket basis for a unique app since Android 3. It is replaced by eBPF since Android Q. So only Android Pie and lower versions are affected. Basically how it works is that a user space program may send the command data to the kernel module, such as asking kernel to tag a socket or untag a socket. So tag a socket basically means that we want the Android kernel to track the specific socket file descriptor and provide network data usage information back to the user space. You may interact with the kernel module by ADB, or you may use the Android API from traffic status or other classes. Cool. So now I will introduce three different scenarios. Open the module, tag a socket, and untag socket, and see how the kernel works. Once user space open the kernel module, the module will allocate two different structures in respect to per UID and PID. And as you can see, there will be only one unique UID data attack data structure, but there might be multiple procedural data structure for every PID, which are essentially linked to the UID tag data structure. And while user space program tries to tag a socket, it has to provide all sorts of information kernel wants, such as like the socket file descriptor, user ID, etc. And the two different data structure will be allocated in terms of the UID and PID again. So first of all, the module will find the corresponding UID tag data based on UID. So kernel will search a global variable called UID tag data tree and find the corresponding UID tag data. Okay. Then a specific structure called tag_ref was allocated and initialized with the tag and the reference count. By the way, the tag is just a 64-bit integer. Also following the similar pattern, the kernel will find procedural data from a global variable and allocate a structure called socket tag. As you can see, the different socket tags are linked together, and they are all from the procedural data structure. So for now, please remember the sock tag structure. Later we will see user-free in sock tag structure. So here is the basic overview of all the related kernel data structures when a socket is tagged. As we mentioned in the last slide, the module will create tag_ref and sock_tag structures in here and here. So while a socket is untagged, the reference count in the tag_ref get decreased, and the sock tag is unlinked and later freed by the kernel. So you may also imagine the basic idea of how the cleanup works is that when user closes the module, all the related sock_tag structure and proc_qtl data may be unlinked and freed later. Since the module was introduced in Android since 2011, there were two vulnerabilities reported to Google in the past. The first one is CV 2016-3800. It's a pretty well-known vulnerability. It's a very important kernel information leak issue for leaking the kernel sock structure address. You may just read the sudo file system, and the arrow pointer is returned to the user. It helps a lot of exploits to make them more stable and easier to exploit the Android kernel, such as like ping pong exploit. The root cause is pretty obvious. If you look at the sequence printf, the format string is not applied properly, so another user may be able to read the wrong pointer address. Well, the other one is a user-free bug on tag Ret2 by race condition due to imperfect logging. As you can see from 2011 to 2020, there are only two vulnerabilities in this module, and the module got replaced since executed by Ret2bpf. So what can possibly go wrong in 2021? The bug was reported by an external researcher early this year, saying that there is a potential user-free under certain conditions. There is no proof of concept or exploitation details provided, but the researchers believe it's impossible to exploit on modern devices because the hardware level mitigation, the user access override, is enabled on kernel 4.14 by default. So usually Android exploit will choose to temper the address limit, so the exploit can use pipe syscall to do arbitrary kernel read and write. But there are a lot of ways to temper the address limit. For instance, you may set up a drop or jump to several well-known kernel functions, and Linux kernel is very happy to override the address limit for you. But with the user access override mitigation enabled, it's not very likely to exploit the kernel in this way. That's why the external researchers believe the vulnerability may not be able to be exploited on modern devices. Thus, the Google Android security team decided to investigate the likelihood of exploitation of this vulnerability and see if it still works on modern Android devices. When the bug was reported to Google, Richard quickly wrote a minimal POC for kernel crash. As you can see, it's very simple. Just tag socket, untag the socket from a child process, exit program, and kernel crash. How is it possible? So let's take a closer look at how untag actually works. Because when a user space program opens the module will create the proc_qtl data based on the PID. Okay, so kernel tries to find the corresponding proc_qtl data structure and then unlink the socket tag and free the socket tag structure later. But if you look at the code, you may see that there is a starting check. If the proc_qtl data structure is not found by PID, the module will just send a complaint here without doing anything, but the socket tag structure is still on the linked list. Since the kernel will still free the socket tag structure, there is a typical user free here. So when you untag the socket in a child process, the kernel module is unable to find the proc_qtl data structure. So essentially it leads to the user free. So you may have two socket tag structure under one proc_qtl data structure, where one of the socket tag is already free, but still resides in the linked list. Okay, cool. So let's see how to exploit the vulnerability in a modern Android Pie device. Specifically, you may see the following mitigations are enabled for Android Pie devices, like address limit check, user access override, slab freelist random, and slab freelist harden. Later I will show a demo on how to exploit the Xiaomi Mi 9 device with the latest kernel version 4.14 for Android Pie with the aforementioned mitigations. Okay, so first of all, if you are not very familiar with Android kernel exploitation, most Android devices nowadays use kmalloc 128 as the minimum size of the slab object. Okay, so the size of the object allocated by kmalloc is actually 128 bytes. The first kernel system we want to abuse is eventfd. As you can see, the count actually overlap the list head in the socket tag structure. Okay, the idea for kernel heap address leak is that once socket tag is already freed, we can spray eventfd to make sure there is an eventfd structure occupy the free socket tag structure. So now you see two socket tag structure linked together, and one of them is actually eventfd structure. Now we untag socket tag in the right side, so the count from the eventfd structure is now overwritten as the address of the list head by unlinked primitive. Okay, so now you may get the eventfd count by reading the pseudofile system. Now we will talk about how to convert the heap address information leak into a special double free in the Android kernel. Basically, a very naive idea is that the way you can get double free is to grab two identical socket tag. So kernel will eventually unlink all the tag and free all of them. So you might get a very nice double free primitive, but obviously the kernel crash because there are several security checks. For example, if we grab a socket tag structure with invalid tag, the kernel crashes because the corresponding tag graph structure doesn't exist. And if we create two identical socket tag structures, the reference count will become invalid, so kernel will crash too. Okay, so therefore the approach to bypass all the security checks is to create several normal socket tag structures and steal their tags. Here is the way I figure out is that first of all, untag the socket tag B from a child process, so you get a user free. Okay, and then the next step is to spray the eventfd to occupy the free socket tag structure. Okay, and then free the next socket tag structure C, and because of the unlinked primitive, the socket tag structure D, its address gets leaked. Following this way, you can also leak the address of the list head. There are also another three different tag structures, E, F, and G, in the linked list. We will talk about them later. Okay, so the key point here is that we have a socket tag address and list head address. Cool. So in order to bypass security check, we now spray first two objects and impersonate the tag. So the original tag are B and D, and now they are becoming E and F. Okay. We also unlink EFG from the prosecuted data to make sure the tag ref and the reference count will remain valid. Okay. We will also have to free these two corrupted objects because the first 8 bytes of the object must be a valid address. Otherwise, the RB erase operation might fail. Okay. Cool. In this way, we may free the corrupted socket tag structure without triggering any kernel checks. We will later use this primitive for performing a special kernel double free. By the way, for devices still vulnerable to CV 2016-3800, exploiting the kernel might be much easier because we can abuse a socket put function in the model cleanup process and corrupt a corrupted kernel socket structure. And if you're doing so, you are following the pattern of the pinpoint exploit or other well-known exploit corrupting the socket tag structure. Here the step 2, leaking kernel error. If you check the size of the socket tag structure, it's 64 bytes. So luckily, a 128 byte slab object can host 2 socket tag structures, and thus we may impersonate the tag G and corrupt another socket tag structure in the same slab object. Okay, so when the model is doing cleanup, it will free the socket tag structure and free the socket tag structure in the middle of the slab object, consequently, which will help us leak kernel error. Okay, cool. So consider spraying the slab at the beginning of the exploit. So and then keep opening a lot of proc CPU info, so kernel will allocate a number of sequence file structures. And because of the double free primitive, 2 sequence file structures are very likely to overlap each other in this case. Cool. So the overlapped event FD and sequence file structures leads to a very interesting result, that the count from the event FD now becomes sequence operation. Okay, and very likely the spin lock overlaps each other. So the spin lock from the event FD still works, and we can read the sequence operation from the event FD by pseudo-file system again. By doing so, we can successfully leak kernel ASLR from midnight device here. So if the slab free list is not hardened, you may build the double free primitive to do kernel space mirror attack. Unfortunately, the mitigation is enabled in midnight device, so abusing the double free primitive directly is not very possible for me. There are also other candidates, such as using the socket put, where you may control the socket structure. I would say it is possible to disable SC-Linux and KPTL restrictions, but it depends on kernel image. Okay, cool. So my approach is to override the sequence operation. So sequence operation contains several kernel function pointers. So tampering the sequence operation might be a keen interest for us. Okay, so let's take a look at event FD again. Not only event FD can leak kernel information to us, but we can also write data to event FD. In this case, we can control the count from the event FD, which is now equivalent to override the sequence operation because these 2 structures are overlapped each other. But since we have a lot of file descriptor which open the CPU info, so the question here is that how can we find the file descriptor of the overlapped sequence file object? So my solution is to override the CPU info operation to console operation, and then read data from every file descriptor. Then we may find the corresponding file descriptor, because one of the file descriptor may print something different. So the next step is to control the sequence operation. We can simply overwrite the sequence operation to control slab object. And initially, we can just fill the sequence operation with something random like Ret2bpf. So we can validate that we can now control the kernel IP from the kernel crashdown. Okay, cool. And as we mentioned before, the challenge here is that how can we craft a sequence operation to control the kernel IP and perform escalation privilege? We might need to split the sequence file structure again in order to ask kernel to use the crafted sequence operation correctly. Otherwise, the kernel might crash. So if the user access override is not enabled, we may use drop gadget in the kernel get stuck off to gracefully temper the address limit. But unfortunately, it doesn't work on kernel 4.14 because the kernel will check the address limit for every syscall, and kernel enables user access override, which is a hardware level mitigation. So we must find another way to properly fill the drop gadget. So here is the ultimate drop, and we also call it the Ret2bpf. And as mentioned by Project Zero, we can invoke an internal function called bpf_proc_run as the ultimate drop. So the basic idea here is that if the second argument is the address of the bpf instructions, then the kernel is happy to execute arbitrary bpf instructions without any counts of verification. So you can do everything you want. So as a consequence, now you can get an absolute kernel read and write primitive. For instance, you may disable the kptl restrict and SE Linux in this way. So here is the drop gadget field to do the Ret2bpf. And here is the results of disable the SE Linux. Okay. So finally, we can get a root shell by execute the arbitrary bpf instructions again, and then handle the crash structure by pure cred. Okay. These bpf instructions are just 128 bytes, so it just fits for a slab 128 objects. Cool. So now this is probably the most exciting part during this presentation. I can pound midnight device in less than seconds, and then we can have a root shell. So now we get a root shell. Cool. So now please welcome Richard for the rest of the presentation.
Now that Xingyu has looked in detail at how he exploited the vulnerability and the problems he had to overcome, I'll look at some of the mitigations that make exploitation here more difficult or impossible, and then move on to reviewing some of our defensive systems that help us find malicious software and exploits. Starting off with kernel mitigations, the first one we will look at is a Linux kernel compilation setting that affects the pointers and the free lists maintained by memory management. Added in Linux 4.14 in November 2017, one of the things config/freelist_hardened does is to XOR the free list pointer in slug caches with a per cache random value. This makes exploiting free list pointer overwrites more difficult, as unless the attacker also knows the XOR value, they don't get control of the memory address. This mitigation has very low performance overhead. The mitigation can be bypassed using the signal FD technique shown on the slide and described earlier. Spraying signal FD context structures allows a mostly user-specified value to be set via the mask argument. I say mostly because 2 additional known bits will be set in the value that is written, so the attacker does not have complete control over it. This does allow the attacker to mostly control the important value in the SOC tag structure, so detection of the list corruption can be avoided. Other kernel structures may allow user mode some degree of control over data at particular offsets. For other exploits using the multicast group join operation as an example of this, see CVE 2017-8890, for which there are a number of proof of concepts available on GitHub. Kernel Electric Fence is a low overhead sampling-based memory safety error detector introduced into Linux in 2020. It detects out-of-bounds heap access, use after free, and invalid free errors. Kfence uses a sampling interval time to determine whether to apply guards to a memory allocation. When the sample interval is reached, the next memory allocation made will be guarded and the sample interval is reset. A guarded memory allocation requires 2 additional page table entries. There is a page of memory for the allocation itself and a guard page either side of this one. The actual memory allocation is made either at the beginning or the end of the page it is in. The remainder of this page is not used for other allocations, but is filled with known patterns to enable detecting incorrect writes into this area. Other underflows or overflows will be caught by the guard pages. Kfence will not detect every memory safety error that happens, as owing to the sampling interval, not every allocation will be guarded. An individual system is very unlikely to apply guards to a given memory allocation. However, given enough systems running it, code paths which cause errors will get exercised with guards applied to those allocations, so issues will be identified. As well as detecting the memory safety errors, moving some blocks out of the normal heap area may affect the reliability of some exploits, as memory layout cannot be so precisely controlled. A common technique in kernel exploitation was to overwrite the user mode address limit stored in the kernel. The address limit was used by the kernel to check whether an address provided by user mode via a syscall was allowable or safe to access, i.e. whether it was a user mode address or not. Addresses below the limit are okay, addresses above the limit are not. If the address limit could be overwritten by -1, for example, then the kernel would think that it was okay for user mode to access kernel addresses. Having overwritten the address limit using an exploit, to read kernel memory from user mode, a pipe would then be created. Next, a write syscall to the pipe using a kernel memory address for its buffer would copy from the desired kernel memory into the pipe buffer. This would be followed by a read syscall, which would read the kernel data from the pipe buffer and place it into the user mode buffer provided. A similar 2-step process can be used to write to kernel memory. The write syscall writes data into the pipe's buffer, then the read syscall reads from the pipe into a kernel address. This exploitation technique was mitigated using ARM's user access override bit. UAO changes the behavior of the LDTR and STTR instructions when they are used by the kernel to perform memory copy operations. For example, those required by the read-write syscalls in the example given just now. If the UAO bit is set, then the instructions behave as privileged load and store and cannot access user memory. If the UAO bit is clear, the instructions are unprivileged and cannot access kernel memory. So, whichever state the UAO bit is in, one of the read or write operations will fail, and the attacker cannot access kernel memory using this technique. This mitigation can be worked around using the Ret2bpf technique described earlier. Address limit protection has also changed in more recent versions of Linux, resulting in the removal of this configuration option. From the explanation of the exploitation process earlier, you may remember the seek file structure was used to help. Overlapping eventfd context and seek file allows Xingyu to use the seek file structure's seek operation member as the eventfd context structure's count member, and therefore leak kernel memory addresses. Later on in the exploitation process, overriding seek operations was used to demonstrate control of the instruction pointer. Seek file has been used in many Linux kernel exploits. Moving it into a dedicated cache would obviously make techniques such as the ones mentioned earlier stop working, as it would not be possible to confuse seek file structures with other structures. This would have some impact on memory usage. Control flow integrity tries to make sure that indirect calls and function returns go where they are supposed to. Without this, attackers can hijack the expected control flow of a program, or in this case the kernel, by changing function pointer addresses or return addresses. CFI is implemented for Android using Clang and is performed at the final link stage, so all information is available regarding function addresses and their callers. This does somewhat increase the link time when building the kernel image. The link took longer than compiling all of the object files the last time I tried it. For indirect calls, the compiler essentially inserts a check on the target address just before the call happens. If the target address is not in the list of allowed addresses for that call site, the kernel panics and the attacker does not get to call the address they wanted to. As shown on the slide, in this case, trying to use the modified seek file operations would have been detected. An alternative way to execute Ret2bpf would have been required. CFI usage in Android has been increasing each year as more OEMs enable the feature in their kernels. CFI is also used in the generic kernel image project, so as newer Android devices start shipping with GKI kernels, CFI support across Android will continue to increase. This kernel configuration setting, which is now required for some architectures for Android, causes BPF to always use the just-in-time compiler. The BPF instruction interpreter itself is not compiled when this setting is enabled, so the code for it is not present in the kernel image. Since the code is not present, it cannot be called by an attacker. As Xingyu demonstrated earlier, if the BPF interpreter is present, then having control of the instruction pointer and some arguments allows it to be called to execute arbitrary BPF instructions without them having gone through the verifier. This mitigation blocks the Ret2bpf technique that was used in the demonstrated exploit in order to bypass other mitigation techniques, defense in depth. The final kernel mitigation, config debug list, is another one recommended by Project Zero, this time by Maddie Stone, which is also now required for Android. After an operation on a linked list element, the forward and backward pointers are checked to ensure that the links between elements in the list are valid. This has a slight performance impact, but means that list corruption is detected as it occurs, which would stop the exploitation techniques described earlier from being used. In conclusion here, there are a number of mitigations which would have blocked various parts of the exploit described by Xingyu. Some of these mitigations were encountered on specific devices during development of the exploit, and these were able to be worked around. Other mitigations that are present on other devices would have blocked these workarounds. Multiple mitigations that would have blocked the exploitation here are required now on Android, so a similar vulnerability would not be exploitable in the same way in the future. Now we'll talk about some of the other ways we protect Android users. Starting off with on-device protection, Android's application verification feature is something you may be familiar with. When an application is sideloaded, for example, the app verifier will check to see whether it's known to be malware. As well as checking for specific APKs, Android can also look at the similarity of an APK on device. Information about known bad applications for the similarity check is provided by Google's servers. This is to handle small differences in an APK's contents which would defeat hash comparisons, for example. This covers the case where a sideloaded application might contain a local privilege elevation exploit to support malicious activities. Advanced protection is an opt-in system that most visibly enables two-factor authentication and restricts application installations to a subset of those available on Google Play. Sideloading is disabled and cannot be enabled. Limiting the pool of applications that can be installed makes users less likely to encounter malicious applications. Moving from on-device to server-side analysis, we have a lot of infrastructure analyzing Android applications. All applications are constantly reanalyzed so that any new detection rules or analysis systems are applied to everything over time. We use static analysis to generate information from an APK and the files it contains, and dynamic analysis to run the application in an instrumented environment to get information about what it does. We also inspect packers and obfuscators to support better static analysis. The graph here shows the proportion of malware apps that are protected by different packers. This sort of data shows trends in the malware ecosystem and allows us to identify when packers lose and gain in popularity, which can indicate that there's a new packer available, for example. Dynamic analysis doesn't suffer from the same packer issues as static analysis, as the application has to be able to run. When an application runs, its functionality can be exercised, and we can see what it does by instrumenting framework and OS APIs and seeing what data it accesses. The long-term objective of any analysis work that we do is to be able to automate the process of extracting additional information or performing additional detection based on what has been learned. Manual analysis and detection doesn't scale well against millions of applications. We also have many machine learning models that take all kinds of data about applications as their input, so additional types of data from applications can often be very useful here as well. Having just said that manual analysis doesn't scale well, it is still an important part of detecting malicious software. We work with a number of other internal teams, from getting initial leads and performing investigations, through to research, enforcement, and education. External researchers submit information about malicious applications or vulnerabilities. These will be investigated and the appropriate action taken. Inside our team, we reverse engineer and analyze malware to understand what it does, writing reports on its behavior and functionality to spread awareness and knowledge around other security teams and analysts. Most commonly, this results in additional detection being implemented using existing systems. Sometimes we work with software engineers from other teams to design and implement new detection systems to fill capability gaps, or to propose changes to the operating system to make it more secure or resilient. Static analysis of software scales better than dynamic analysis. However, it can be very difficult to understand what an executable actually does, purely by using static analysis. The image on the left shows the control flow for a very simple exploit sample, CV 2016-5195. The madvise and seek-right loops can be seen in this minimal implementation. The image on the right shows a larger, different exploit and the apparent control flows there. The image in the middle shows control flow of an obfuscated function as displayed by IDA, which is considerably more difficult to understand. Even a simple piece of code, such as that on the left, becomes harder to read when it is obfuscated. Dynamic analysis, however, lets you see what the code really does, providing you can get it to run and perform its malicious actions. Exploit samples are generally straightforward in that they try to exploit the device. There may be checks for whether the device is supported, particularly if the exploit relies on knowing memory addresses or offsets, for example, but these can always be knocked out, provided you don't mind taking the risk of crashing your test device if it is vulnerable. Local privilege elevation exploits, often referred to as rooting, generally need to interact with the OS kernel. Obviously, if an exploit requires a particular device driver, you have to have an appropriate device to run it on. If you can see what the exploit actually asks the kernel to do, then you can start to understand what's happening and then look to see whether it is for a known vulnerability. Ret2bpf, one of a number of tracing or monitoring mechanisms for Linux, allows monitoring of kernel calls and the parameters they are given, which can be used to look for evidence of exploitation behavior. The exploit described earlier by Xingyu relies on various kernel heap sprays in order to control use after freeze by manipulating the contents and layouts of a kernel heap. If we can detect that a spray is occurring, or seems to be occurring, maybe we can detect when exploitation is happening. Kernel heap sprays are performed typically from user mode by allocating or releasing large numbers of particular objects, for example, files or sockets. As well as looking for generic evidence, such as memory manipulation and layout control, some specific kernel interactions that have been used to exploit different vulnerabilities over recent years are shown on the slide as well. These are from several different exploits. Some are highly specific, others are more general techniques. I'm actually going to show behavior from CVE 2018-9568 for the detection video. This is better known as WZ Router by Thomas King. The technical paper has a similar manual analysis on the CVE 2021-0399 exploit. I have a couple of terminals on a phone. The one on the right is the monitoring software, the one on the left is where I'm running the exploit. You can see the exploit starting up and behavioral events being shown on the right. The device isn't actually vulnerable in this case, but the exploit tries anyway. We stop monitoring after a short period, then I switch to another terminal to download the save trace and put it through the analysis software. So you can see here a number of events have been highlighted. Loops of syscalls, you should be able to see a few ioctl and close call loops. If we move further back, we get to a series of loops creating sockets. You can see there are several different threads, each creating hundreds of sockets. Here we are looking at some of the different thread IDs. As you can see, each thread is creating several hundred sockets before finishing what it's doing. Moving further back in the trace, we can see some more socket and close loops, and then if we go back a little further, we can see some clone calls where the threads are being created. The behavior seen here, where thousands of sockets are being created and closed, is unusual and likely indicates that kernel heap structure manipulation is happening. It turns out that CVE 2021-0399 could be exploited on devices with the UAO mitigation. If you're investigating whether a vulnerability is exploitable, keep looking for workarounds or alternative techniques and talk to people. The more knowledge you have about what's available and what it can do, the more likely it is you will be able to come up with something. Xingyu encountered a number of problems developing the exploit here, but with a lot of work, plenty of heap manipulation, and help from other people, he was able to overcome them on his development devices. The workarounds used were themselves defeated by further mitigations, which you can find on current and future Android devices. We mentioned the generic kernel image project earlier. Essentially, this means kernel updates will get onto user devices faster, as there is less effort involved across the ecosystem in applying security updates. Thank you to two people without whom this work would not have happened. Jan Horn for discussing exploitation techniques, suggesting workarounds for mitigations, and then more mitigations for the workarounds, and ZY Joe for donating his MI9 phone to be used for exploit development and testing. Finally, thank you for watching.